Forming Magazine, and I'm pleased to serve as your moderator today. Before we get started, just a few quick notes about today's GoToMeeting session, which is being recorded for archiving. Therefore, all participants are in listen-only mode. The speaker and other listeners will not be able to hear any audio from your site during the program. However, you do have the ability to communicate with us throughout the program by submitting any questions you might have using that question box, which is located in the right-hand control panel on your screen. Simply type your question to an organizer as selected from the drop-down menu. Also, before we get started, one last note. I wanted to let everybody know that a recording will be available of this webinar within the next few days on our website at the magazine, as well as on the website of Cimatron. So now it's time to begin today's webinar. Our speaker this afternoon is David Lindeman. David is an application engineer with Cimatron, and he's here to discuss how simulation software and the virtual press room can help designers correct many of the problems related to die rework and rebuild before the die hits the press room floor. So please welcome David Lindeman, who will take us through the virtual press room.
All right, thank you, Brad. Just a little bit about Cimatron, the company I represent. It is a worldwide leader in CAD/CAM, dealing tremendously with the die, tool and die making process. We've got over 33 years of software experience tailored just to that industry. And as you can see from the pop-up, well over 40,000 installations. A private survey firm did some checking on us and found that Cimatron customers deliver their tools faster to market than anyone else dealing with using CAD/CAM to deliver their tools. So in this webinar today, we're going to talk about the pains and issues that are faced in the die making process. Typically, you might think of things like predicting spring back and whether or not a part is going to be formable. When you get the CAD data, can you tell if you're going to be able to actually bend and move the metal into the right places? And then adapting the die so that it's deformed to match what's going to happen when the part springs back. There are a lot of decisions that are made when building a die, things dealing with pressure pads, draw beads. All of these things together, the pilot holes, all of these paint a picture of what the die is going to look like, how it's going to operate. So as we add one factor in, does it change things? The important thing is that we'll be able to consider all these factors together to assess whether the part is formable and how we can deal with issues such as springback. Of course, I don't need to tell you why springback is a pain. It's difficult to predict how the part is going to snap away from the die steels. It's also a challenge to get the information you need. Typically, you'll put on a CMM and digitize points to try to understand how the part has moved. And then when you've done that, how do you adapt the tooling? How do you adjust the tooling to match it? Perhaps you have heard of the expression tape and grind. You have to tape up the die to add material and then grind clearance so that you can get the part in and out of it. How many times do you have to take the die through a tryout to see if the changes you've made are making the effect on the part that you're looking for? All of this takes time, and when you're dealing with a complicated die, it can be very costly, very time-consuming. In the end, your die design is really chasing after the actual die. You're trying to get the die design to be on par with what you've done to the die so that your data matches what the actual die looks like. And then with formability, all too often, the experience of the shop will put their heads together and look at the part and decide how they anticipate the part is going to be made. In fact, they may even go through a couple of iterations of that design expecting it not to work right. They want to see how it fails so they know what to do to make the adjustment. The part could wrinkle, the part could tear. All in all, we're talking about reworking a die, sometimes several times, in order to get the results that we're really looking for. So the question that could be asked then, all this work, has it been anticipated? Was that cost included in the initial quotation? Talking about the expense of replacing your die steels, having to work overtime, all those redesign costs. Say nothing of the costs that it could incur your business because of a late delivery. All these things are huge factors that are affected by getting that part or getting that die done in a way that's quicker than going through several iterations, several tryouts. So what we're going to go through today are examples of some real-world issues basically there's some things that we've run into, the problem areas that we've seen that I've designed into some parts, so they're not what you call real parts from real customers. I wouldn't be able to use their data anyway, but the idea is we've captured those problem areas so that we can take a look at it. You're going to see too how we're going to use simulation to find these things and to resolve these things. That introduces us to the term the virtual press room, as if I were doing a die tryout on my computer screen to see if the part's formable. In all, you're going to see about 20 simulations through this presentation, and I estimate each one goes about 3 to 5 minutes to actually calculate on my computer. So it just stands to reason then that we wouldn't be able to show you everything live here, because all you would see is the simulation time. And in all, I estimate it took about 6 hours to go through everything you're going to see when it comes to making the decisions, looking at what happens, and then making adjustments. So here's our example. Simple crash die. It's not overwhelmingly big, 28 by 24, about 6.5 inches tall. And we're going to work with some mild steel, 14 gauge, so fairly flexible, fairly easy to work with. Now as we go through the presentation too, I'll show the menu screens for our Cimatron users who are watching so they can see what the functions are and what you can do with the features in that function. For instance, here I'm going to take a blank. Basically I'm working with the part surfaces on the die side of the tool, those red surfaces. And the idea of the blank is to flatten it out as to what the predicted 2D blank would be, just of that part. One of the biggest factors, of course, is knowing what material we're working with. So an extensive library of materials with each of its own unique properties is built in, so it's just a matter of pulling up that material to see what's going to happen. It will make a huge difference, as you know. Stainless steel is not going to react the same as mild steel. And there are some steels out there now with a hardness to it that rivals the hardness of the die steel that's forming it. So it makes a huge, huge difference to be able to select the right material, not to rely on just mild steel all the time if it's a different type of part. Looking at the result I get from my 2D profile, right away I see an area of concern where there's a loop. That tells me that metal is being stretched in 2 different directions. So there's going to be an issue involved in dealing with that. Move on to next slide here. Okay. Here we see where we're going to now look at some analysis tools, and you see the menu highlighted. Thickness strain analysis is going to show me the percentages and also the thicknesses of that material as it gets bigger and thinner going through different strains. A safety zone is the one I prefer to work with, which shows the wrinkle tendencies, the tear tendencies. It also gives me that same percentage information. And then we'll also look at the springback analysis. So here's the safety zone analysis, as you can see it diagrammed. Looking at that trouble area, sure enough, like expected, there's a strong tear tendency. Most likely that's going to fail in that area. Whereas in other areas, there's a very strong wrinkle tendency. The problem also exists in that they're very close together on the part geometry. And then looking at the springback, run this analysis, we find that it anticipates the trouble area to be about 103 thousandths out of springback. So all I've done is run the blank function and then run a couple of analysis functions to gather this information about my part. Already I have some initial findings that I need to consider. The wrinkle on the top, the area that's going to tear down in that lower corner. There's an area that's very strong with tendency to spring back. And the geometry of all this is very close together on both sides of the part. So now that we know all this, what do we do? Well, it's very common to put a binder on a part like you see here, shown in the red. If there's not enough material going into an area, we'll put a binder around it so that we increase that material. It has material to work with. Also, it improves the area for metal flow. So what you see diagrammed now, this red area with the binder, that's what we're going to use as we go back through these same simulations. So we recalculate the blank, and now we see a nice clean outer boundary. That looks good, so I know I don't have that material stretching in 2 different directions. Now when I go into my safety zone analysis, I look at that trouble area before where it's torn, and now I see it's good, it's green. So I'm elated. Already the binder has shown some positive feedback in helping me to make this part and form it right. However, it came at a price. Now the wrinkle area has increased in size quite a bit. So that means now I've got to deal with the wrinkle area. A couple of functions when we talk about blank in Cimatron, blank on binder, the blank function I previously mentioned, they allow you the ability to incorporate die features, things that you'd put into the die to actually make the part formable, such as pressure pads, draw beads. The blank holder is important. We're going to look at some of those things now and consider how they're going to help us as we continue our prediction of what the part's going to do. The pressure pad is designed so that it's going to constrict the area that's in between where the pressure pads are, that wrinkle area. I want to reduce the flow into there so the material doesn't get there too quick and start to wrinkle. Here's the adjustment you can see where pressure can be adjusted so that you can manipulate how that pressure is going to affect the part. And again, the idea is to add constriction into that. So looking at the result now, here you can see that that wrinkle area is gone at about 10%, which is still pretty significant. But compared to what it was before, you can see that it's quite a bit reduced. So right away that pressure pad has had an effect. And you can see it's reduced along the top of the part. There's a lot less dark blue on that top curve face, whereas going down the sides it's about the same. So we can see the effect that that pressure pad is having. What else could we do? Another typical way of handling issues like this would be to put draw beads in the part. What we're asking for, what Cimatron is asking for, is the center line of the draw bead, and then we add the tension to it, how much pressure we're going to put on that draw bead. Using that, we get this result. So the draw bead looks good in helping the part form. Now I'm down to 4% in that wrinkle tendency area. So the numbers are getting better. But I've got a huge problem with a tear now. You can see how I'm chasing one problem after the next, and I'm adding one element to the next to see how they accumulate and help me work with the die, help me make decisions on how we're going to continue to design it. I can't live with that tear area. For one thing, it's into the part zone, so I know the part's going to be weak or too thin if it doesn't tear, but if it does tear, it's going to be scrap. Plus, there's safety concerns. Why do I want to tear that blank and create a situation that could actually be harmful to someone? The wrinkle zone is reduced further, like you see here, but it came at the cost of strain on the part surface. So what the designer may do, here we'll rerun the simulation. Let's move that draw bead further out away from the part geometry. It comes at a little bit of a loss. You see that my strain has increased up to about 5.8%, 5.9%. Also adjusted the pressure a little bit, and you can see it has reduced the tear. Perhaps we could go further with our adjustments. Such as here, this function does give you the ability to control how much pressure you're going to put on that draw bead and in the key areas. On the back of the draw bead, the end of the draw bead, close to where the wrinkle is, I'd have a higher pressure because I want to constrict the flow of material in that area. Whereas out further away, it's not near as significant, so I'd reduce the pressure. You also have the ability to do that with individual pressure pads. They don't all have to be the same amount of pressure. You can control how much pressure you want at each pad area. And when I do that, I get some very nice results. You can see the strain is now under 5%. The tear zone is just about all but eliminated. There's a few areas, but all in all, I'm liking the results I've seen, especially compared to what I started with. Got a formable part, maybe a little bit of wrinkling, but all in all, it looks good. However, if you noted, there's a key factor to this design that has not been included yet, and that's the pilots. Clearly, the part is intended to be formed by dropping it down on the die with the pilots locating and somewhat holding it, and then it's formed. Those pilots are going to greatly reduce the amount of flow that the material would have in those areas. Now we go and pick those pilots in part of our simulation, introduce what factors they're going to be, and you can see a strong tear area is around those pilot holes. Also, by including the pilots, the tear area along the bead is back. So I'm adjusting as I go by adding these elements and tweaking them. The wrinkle zone is greatly decreased, but I can't live with the tear. So what can we do now? Well, thinking out loud, since I see so much of the tear in the draw bead area, maybe what we'll do is move the pilot holes further out, and we'll start tweaking that draw bead again. Notice my wrinkle tendency is way down now. It's like 2.6%. And by moving the pilots out, I've also moved that strain out away from the part. So I'm seeing some good results already. But when I go one further and take the draw bead off entirely, the tear area in that zone is gone. Yes, the strain's increased a bit, back up to 5%, but you can see that's had pretty good results in telling me that the part's not going to tear. So it helps me to stop and think about what I'm doing as I'm doing it. Imagine yourself out there at the press. You set this die up for the 5th time now, and you smack it, and sure enough it tears right where that draw bead is at. So now your frustrated foreman says, that's it, I've had enough of this, I'm sick and tired of taking this die off. He goes and gets a disc grinder and he just grinds that draw bead down because he knows that's going to work. Is that going to be the way you want to solve the problem? Well, clearly it makes more sense if we can control the process and look at what we're doing here on the computer screen. We're going to have a better product to take out there when we start doing our die tryouts. So thinking about what that pilot is doing, since it's really constricting the material flow, let's take the pilot and line it up in line with the wrinkle area. Here it's reduced the wrinkle area just by moving it, shifting it that little bit, those few millimeters, it's reduced down to 3.2%. And looking at the tears around those pilot holes, I'll ask myself, well, what are the tears going to do? It's to be expected that you're going to have tear areas on the pilot in this sort of design. That's just how it is. But I don't see it near the part edge, and I don't see it where it's necessarily going to hinder my ability to take this and put it into a trimming die. I've still got good clean edges along the pilots down toward the front of the binder. You know, the way you see this part clearly can only sit in a trim die one way. Is it going to be pushed up snug enough? Well, someone may say, yeah, that's fine, I can live with that. Others may say, no, I want those pilots to be clean. Maybe I'll repunch those pilots so that I have a new clean pilot for my trim die. All in all, you get the idea that it's a lot easier to make decisions like that when you've got the information in front of you and you can see how the sheet metal is responding to the things that you're putting into the die. Maybe I would have gone further with that too, snapping back to this picture. You know, looking at the area right along through here on the back, I see some blues, some possible wrinkle tendencies. Well, I need to allow a bit of a binder out in that direction and constrain it that way so that I can get that wrinkle area away. Is there something I can do further, perhaps to reduce the overall size of the binder, cut down on my material usage? There's a lot more questions we could keep asking and continue to go with in this direction if we wanted to. But at this point, let's introduce now what's going to happen when we include some spring back. Now, we looked at the part earlier, and when we analyzed it, we saw we had about 103 thousandths of spring back down in that little flange area. If we rerun it again and include the binder, you can see the results here where it's been reduced quite a bit, and the spring back area is now well pushed off the part. So comparing the two, maybe in my own mind now I'm elated. Well, look, I've done all this work with the binder. I've gotten the part to be formable, and wow, it took care of my spring back issues, didn't it? Well, let's think about it. Obviously, we're going to take this part, binder and all, we're going to put it in a trim die. When I trim the binder off, what's the metal going to do? Well, it stands to reason then that it's going to release tension in that metal, and that spring back is going to take on the characteristics of that first simulation, isn't it? It's going to look like the part because it's the part now. The binder is no longer holding it in place. So this shows us that we have to factor everything together. I have to be able to put my pressure pads in there to control how the metal is flowing, but at the same time I have to know what the results are going to be on the final part with the spring back. I have to take the knowledge of the part spring back and now apply it into this crash die. Adjust the surfaces here so that I get the right part after I've taken it to the trim die. So again, so you can see what's happening. We've incorporated these pressure pads, and that's going to be a factor then in understanding how the spring back is going to change. It'll be a different spring back condition if we don't put in the pressure pads, because it's right there on the part. Whereas other features that we've dealt with are not on the part itself, so that they're not going to be incorporated into what happens when the part does its spring back, such things as the pilots. On the right, you can see in the pull down right where we can get this particular function. It's called the spring back deform, and it's very powerful in how it helps us to adjust these die surfaces. So looking closely at this, you see some white fuzzy lines on my die surfaces. What we've done is, behind the scenes, we've taken the measurements of what that part looks like originally and where it's going to go with spring back. And basically it's nothing more than a couple of STL files that get compared one to the other. But it gives us a linear distance from point to point. We can use that information and now bring it in like you see here, where we're going to adjust the points. So it's a lot more than a pretty picture. It's generating mathematical data that we're using to compensate the die steel. Since it's adjusted out, since it recognizes how the part is going to spring out and away from the die steel, what we need to do is take that distance and take it in the other direction to deform the die steel in, so that the effects we get is going to be compensation in the direction when the part springs. It's going to spring to where it's supposed to be. It's going to spring toward that finished part. Here you see it taking place on the computer screen in front of you. Instead of going through and digitizing points afterward, it's almost like you're doing it right here, right now. So let's look at what happens here. I've got now in yellow is the expected part with the spring back. And we've taken the part surfaces, the die surfaces, and we've compensated them for the spring back. So you can see how they've drawn away from the original design boundary. In fact, you can see we didn't pick the pilot holes, so you can see where they've moved a bit as well as those part surfaces draw in while being deformed. What do you think? Do you think we need to include the pilot holes in this? Well, they're not going to move. So we'll pick those now, run the simulation again, run the analysis again, and say this is a fixed constraint, they can't move. Let's see what we get. You can still see how those part surfaces are being deformed in. It's still taking the data of the part itself, and it's still pushing those surfaces in just like it would. We're just saying don't move the pilot holes. So there's a flexibility there that it gives us where I'm not totally redesigning everything. I really need to know those pilot hole locations, and I really need to be sure they're not going to move. So that's a crucial part in understanding how the die is going to hold its form while I do this deformation. So here this time, now having put the pilot hole in, looked at the result, I've changed the simulation again, and this time instead of using 100% of the expected spring back, I'm only using 80%. Now this is just a general guideline rule. You can work with it that way if you want. You don't have to. Why 80%? Well, in my discussion with software simulators and other people who have been using this product for a while, own personal experience too, it always makes sense to try to keep the die steel safe no matter what you're doing. So if I'm going to cut it and then try it out, I might as well make sure I got a little more steel left there that I can cut it back down if I want to tighten it up again to get more of the spring back factor involved. I can cut it, prove it in my own mind, and then recut it to finish it. And again, too, it varies on the type of material that you're working with. Some simpler materials, it's not so bad. Other materials, softer materials, other materials, you might want to be sure that you've got everything accurate before you go further with it. Now at 80%, well, first let me explain this diagram, and then we'll follow this thought here. You see in green, this is the part that's predicted with Springback, and the red's the finished part data, the actual part data you got from the customer. We'll call this the virtual tryout. Now that I've deformed the die faces, I'll run the Springback again using those deformed faces to see if when the part springs back, it's going to spring back to where it should be. It's going to spring back to what the finished part should look like. When I do that, I can take that now new part and compare it to the original part data to see if I've got that accuracy or not. Looking at the part with the red and the green, you can see a number of areas where the colors are bleeding through. So they're just about coincident. They're very close. But in the troublesome area, the area that I know I'm going to deal with Springback, I need to take another closer look. And when I zoom in on this area and take a measurement, I see I'm still about 13 thousandths away. Now that's a far cry better than the 103 thousandths we were originally dealing with, but it's still 13 thousandths. So in my mind, I'm thinking, doing a little bit of math. I've used 80% tolerance, so I am forcing the part on one side of its overall tolerance. And then in that area, I'm adding another 13 thousandths. So it stands to good reason that right now, while staying steel safe, that corner is still going to be out. Do I go ahead and cut the die and then form the part, check it to confirm that, or do I feel comfortable already knowing that that's going to be further away to go ahead and make the change? In this case, even after having deformed the part, we'll now go in and we'll locally modify that troublesome corner. So it's a matter of taking that point basically, and I'm going to push it an additional 13 thousandths in. You can kind of see that. I just noticed today that when I typed in my Y value, I typed in the wrong number. That's why I see negative 3 thousandths. It should say negative 13. But right about where that particular point is, right here, source 3, that would be the point where I'd push it in 13. And I would also work my way up and down along that edge so that I can control how much that's moving. So it doesn't drastically go from 0 to 13 and give me any sort of squiggle, but I'm controlling it, smoothly changing those values. That's why I put in a lot more control points. You see 3 more control points in red. Real practice is I would probably put in more so that I can get that nice smooth edge in there like I like. Okay. So a couple of things to look at here. Because I've done that, you're going to see that the gap is increased along that area, and that's something that now I'm looking at filling in that gap, finishing off that tool design so that I can go ahead and cut it. But also, if you've been observant, you might notice that when you see these red and yellow slides, which the red being the die steel, the yellow being the predicted part of Springback, that sometimes they're not exactly even left side to right side. They're not exactly symmetrical, even though this is a symmetrical part. What I did was in the background here, I moved that one pilot hole about 2 millimeters. I might do that in a part that's not exactly symmetrical because I want to take the blank and drop it down correctly. I don't want to flip it over accidentally and make the part wrong because the blank was flipped over. So this is something to think about. You can see that just that slight adjustment in moving the pilot did affect the outcome of the calculation. It affects the total deformation Springback, which tells me maybe when I do offset a pilot, perhaps I'm going to pick one that's further away from the part that has less of an effect, or just put it in an offset location where I know it's not going to cause a problem to the deformation. Something to think about, as we look at the detail level that we're getting into working with this. So we pushed that corner back a little bit further. We stayed 80 thousandths steel safe, or 80% steel safe. With that, we'd be ready now to go back and finish up the die side by blending in the areas from the binder that we deformed to the tool steel that was originally designed. At this time, I might go ahead and drop in the draw bead as well if I had chosen to use that. Actually model it up now as 3D. When I showed you the draw bead earlier in running the blank function, we asked for the center line and we asked for a pressure. So really it's kind of a predictive tool for a draw bead. Wherever I go, it seems every shop has their standards for draw beads, how much distance away from the part, how much clearance they want, how big they want it. So it's not like you're constricted to using any specific type of draw bead. You can make it the way you want. If I were concerned about this now and wanted to see, well, I got a 3D model draw bead, let's see how it actually looks, go ahead and run it through the analysis again. It's going to act like the metal's going to act like the metal, and it's going to be constricted by the draw bead, just like you would expect. So we go ahead and run it and not use that predictive draw bead like we did before. So we threw a lot at you here in just a few minutes. Those are a lot of simulations. We tried to condense about 6 hours of work so that you can see how all these tools work together. Again, the idea is we want to look at the formability of the part and really analyze it and understand it so we're not tearing and wrinkling. And if we can find those areas ahead of time and improve upon them, then we've cut out a die tryout that would tell us otherwise. So we're actually testing and proving these things as we go while we're doing our simulations and building the die design. Also, we can't ignore spring back. We have to make adjustments understanding how it's going to affect the tool. And again, can I avoid a needless tryout by deforming the tool now in this environment in my computer and considering that like a die tryout? All this is because we want to avoid die tryouts and we want to avoid having to redesign the die over and over and over again. All that's very timely, very costly. But the key to this, the point that really we want you to take away here is to see that saving money is the issue and reducing our time to build that die. And we can't do it unless we really consider all these factors together. I hope I've illustrated to you how one little addition in your design thinking, one addition like a draw bead, moving a pilot hole, can affect the overall outcome to your advantage or your disadvantage. But being able to prove it on the screen, here you've got something that you can sit down together with and look at and say, this is the best way to go about tackling the job because we've considered this, we've considered that, and this is predictively what is going to be the best solution for our first tryout. Will it take away all die tryouts? Well, can't say that, but why not take away those that are the needless ones? So I appreciate your time and attention to this. I hope that I've given you some things to think about, and hopefully it's helped you to think about what you can do in your design process. Hopefully it showed you some tools that perhaps too are things that you can use. So at this time I guess I'll turn our attention back over to Brad, our moderator, and see if he has any questions or anything that you would like, comments that you would like to make.
Thanks, David. Yep, we definitely have some time left for questions. If anybody has a question, please go ahead and use that control part of your control panel. David, was this an actual part or something that you came up with yourself?
It's something I came up with based on an actual part. I added more to this so that I have more problems in it, but at the same time I wanted to keep it simple so we could focus in just on those key areas. So you would have to say the correct answer is it is a part I came up with.
Okay. Do you want to describe a little bit more about some of the other tools that Cimatron has for die design?
Sure. We've got tools that help in building the strip. It's not, it matters, tools like helping you do simple 90-degree unbends to more complicated unbends. Maybe there's a bend condition where I can't take it right to flat, but I've got to unbend to a curved, twisted face of some sort. We can do that. It's what we call a blank on binder function, which I kind of talked about just briefly earlier. Mm-hmm. So all those tools also allow the predictive tools of you're looking at spring back and the forming problems. Those tools then can those features now can be nested. You got nice tools for nesting, for extracting punches, looking at the pressures that are needed or that are created by those punches, whatever pressure will be. Also, in building up the overall strip, nice tools for developing the strip so that you can quickly put together something for a prog die. So quite a bit different from the example I gave you, this crash die, where we talked about blanking and trimming dies, but a progressive die where you go step by step. Nice tools for building your carrier, and then finally also some nice die design tools where you can put an entire die set around the strip, size it accordingly, extract all your punches, and make your forms fairly quickly. Not only for quoting so you can get your overall steel sizes, but also so you can use it in your die design itself. Right. That sounds like a good subject for perhaps another webinar sometime.
There you go. And it's all of it's integrated, right? It's one tied together manufacturing solution.
Yes, exactly.
Okay. Can you talk about the material library? How in-depth is it?
It's very in-depth. You can add more materials, or we can support you with that and adding materials. Basically, you put in the material and you have to know the material properties. Its tensile strength, things like that. And then currently already, though, there are hundreds of materials already built into the system. So if you have a unique one, you can put one in, or you can use what's already there, which is very extensive. Okay. Stainless, aluminum, you name it.
Right. And if you do a model for one material and the material changes midway through the program, how complicated is that to change the material properties?
In that case, you just tell it to resimulate using a different material. Or it could be like also changing the thickness, changing your gauge size. That would also affect it. So you can make those adjustments, get your simulation to see what the part's going to look like or how the blank size may change, and then go from there, continue on from there. That may mean maybe adjusting some of your punch sizes, or it might mean, like the example we looked at, maybe changing my binder a bit, making it bigger or smaller depending upon what the case may be.
Does the software have any kind of built-in intelligence to maybe recommend different materials or thicknesses or any of the parameters as you're going?
You can teach it. I mean, it will check the part and it'll give you your thickness. It knows that. You can say, I don't want you to put a nesting layout in with anything less than 1/4 of an inch distance in between my parts. Things like that. So as far as intelligence beyond that, where it's making more major decisions for you, it's going to require your input on some things. Like you need to tell it how far away you want your draw bead when you model it, that kind of thing.
What about adding in lubrication? Adding different types of lubricants and coefficient of friction?
Yeah, that's a good question. Right now we don't have that built in to the system, but that would be something well worth looking at. Let me check on that and see if our partners have anything with that.
Okay. And types of files that can be imported, any restrictions there, SolidWorks?
We have numerous direct translators from all the major softwares, plus this industry standards like STEP, SAT, still see IGES every now and then, but it's all there. Parasolid, all that's there.
Okay. What about understanding the effect on spring back of heat treatment that might follow? Is there any way to predict that?
So you would stamp the part and then heat treat it and see how it would change? Is that the question?
I believe that's the question. If the person that asked the question, if that's not it, go ahead and kind of read. Okay. Yeah, he says that is the question.
Okay. To that degree, no. That would be like understanding, taking the tool steel, heat treating it, and trying to understand how much more bigger it got. Right. We don't have that level of predictability when it comes to the heat treatment. So typically our die builders will make it slightly oversized, leave grind on their die tools, and then once they get it back from the heat treat, grind it off.
Okay. All right, this is kind of a long question. I'm just going to read it as it's written. In the cost analysis process for quoting, how do you know how many iterations to assume, or do you have a typical number of iterations based on similar types of tool designs, and he's asking this question because it could depend on the experience of the designer, impacting the number of iterations required.
Sure. And hopefully, like with the example we went through, started out not knowing how many iterations I'd need. And I just kept track. It happened to be I went through about 20 on this particular job. I could have gone a completely different path and said, no, I'm not going to put pressure pads in until I absolutely need them. Let me see what the draw bead could do. So a lot of it's going to depend upon preference too, not just experience. Both those work hand in hand. So I can't say throw a part in that says you're probably going to need this many attempts at it, But I would think a good designer, even who's got a lot of experience, can say, yeah, I'm going to need this, I'm going to need that, I'm going to put it here. And his first guess may be extremely accurate. He may just tweak what he found, as opposed to going one at a time like we did in our example. So I guess I can't really give you a definite answer on that except to say, try it and see what you get.
Okay. You can 3D simulate with your software, right?
When it comes to 3D simulation, I can do a 3D simulation of the tool motion, whether it's the die opening and closing with any actions. When it comes to a 3D simulation of part deforming, that we cannot do. We can give you the start and we can give you the finish. And the reason is because we cut the price, so that is the expensive part of this type of software, is that 3D simulation. Right. So that's the part that currently is not included.
Right. Okay. When you have seen that a particular material is declared not formable due to the thickness of the material type, I'm sorry, when have you seen that a particular material is declared not formable? The thickness or material type. And if we still try, will we still see cracks, even though it tells you, once it tells you that it's not formable?
Yeah, when you start getting into that, you're talking about the design of the part. Like a good example might be they give you way too small a radius or way too thick a gauge, and you're going to expect to see that thing to crack. Well, in that case, it'll show you what's going to happen, and you can take this information back to the customer and say, look, we know with our experience and what we're seeing, you can't form the part the way you've got it designed. You have to give some consideration or allow some considerations in these key areas, such as the radiuses. It is what it is at that point. The material is going to act like the material. So you can make adjustments to the gauge thickness, the material type, all that, but I know that that's the kind of thing you have to really go back to your customer on to get his approval anyway.
Right. A couple guys asked kind of the same question. Can you account for process variables, forming speed, for example?
Yeah, that's a good one.
Yeah,
with like a deep draw part, the slower you get, the easier the metal is to move. You're not likely to shear it so bad, that kind of thing.
Right, and you're going to generate less heat.
Right, less heat. That part of predictive intelligence, I would say we do not have.
Okay.
I can, leave it at that. We can't do that yet.
You showed us using the center line of the draw bead. Can you do modeled draw beads in the designs as well?
Sure. Yeah, if you want to do that up front, you sure could. And then you don't use the center line option. You just go ahead and do the part, the deform stuff, or you do the blank, include those draw bead surfaces, and see what the pressures are or what the strains are at that point. Because at that point, metal's going to act like metal. So whether you've got it drawn in or not drawn in, if you draw it in, you've got a pretty good idea what the actual true metal shape is going to be like.
Right.
Versus the one where you're just kind of on the fly saying, yeah, I want to throw a draw bead in here, what's going to happen?
Right. Okay.
Yeah.
And I assume you can support progressive dies as well as
absolutely.
Development, right? Okay.
Yeah. A lot of it we talked about with the strip development tools and the other, die design packages. We have full catalogs for all the componentry that you'd expect to find out there in the market for Danley, Dayton, those sort of suppliers when it comes to punches and you name it.
Mm-hmm. Okay. 5-axis capabilities?
Yep, that's included in our NC package. Yeah. It's nice too. It's a lot of customers using it.
Okay. How about specifically orange peeling as a result? Can you predict the orange peeling?
Specifically, no, I cannot.
Okay.
Yeah. That's a good one.
Yeah, common fault.
Yeah. Oh yeah. Spray more lubricant. I don't know.
Okay. Okay. Any more questions for David? Learning curve. You want to talk a little bit about the typical learning curve that you see from your customers?
Well, we got a brief view of what the menus look like that I put on the screen, so that is a big help in someone learning the system because he's looking at a die function as opposed to a CAD function. You know, so when he goes to blank, he knows what he's looking for, how to make that blank. All right. Mm-hmm. It's just a matter at that point of knowing where the button is and where to find it. Mm-hmm. And we offer a 2-week class to get the basics down. I believe it's 2 weeks. And then further classes for specifics such as die design or sheet metal forming, things like that. You know, and it can vary between on-site or coming to our classroom to get that kind of training. And we find that I'd say within, like I have to go back to my own experience learning it and also guys I've worked with, I found that some have picked it up as soon as a month, where they're starting to create stuff that's going to go to the shop floor to get cut. Others may be a little bit longer. If you come from a background of a 3D CAD modeler, it is easier. And I say that because I see guys who've run 2D systems, AutoCAD-like systems, sometimes have a little bit more trouble with the whole 3D world and the concept. You know, they think in terms of layers, I guess. Mm-hmm. Once that hurdle is crossed, though, then it's a lot easier for them to pick it up.
Mm-hmm. Okay. How about supporting component libraries for European components like Fibro and Agathon and others?
Oh, yeah, we have a full Fibro catalog. We got a bunch of others, Sumis, we're like, you know, Eastern or Oriental, and then we got, what else, Missenberger. We got a bunch of others in there too. I can't remember exactly all of them. But as you can expect, it's an inch and millimeter. Your choice of how you want to work, whether it's in an inch environment with millimeter components or millimeter environment with millimeter components, you know, it's however you want to work.
There you go. Okay. All right, good. Any final questions for David? Otherwise, we'll wrap it up. All right, I guess that's about it. David, thank you very much for your time today, and of course, thanks everyone for attending today's program.
Yes, thank you.
We hope you found it to be valuable, and again, please remember that an archive of the webinar will be available on our website and Cimatron's website very shortly here within the next couple days. David, you have a screen that has your email address on it. Should people want to get in touch with you at a later date? Again, thanks everybody. Thanks David and Cimatron, and you may close your browsers now. Have a great afternoon.